Alright, so this week we're covering number systems in general. So not just for MATLAB, we're covering basically different types of systems that all computers have to use in order to manipulate, store, and play with numerical data, okay? But before we get into that, I thought I'd just like to talk about some of the stuff you did in this week's lab. So it really involved the first two tasks, developing an algorithm to compute the factorial of a given number. The factorial is just a product, right? It's the product for 5 factorial of 1 times 2 times 3 times 4 times 5. So it was an iterative process, and the best way to do it was using a loop. And we know to do that loop, to do a loop that we know that we're going to iterate at a given number of times, we should use a for loop, right? So we should use a for loop, and part of the lab involved actually storing your results partially inside of a vector that would grow over time. So some people had some problems with that as well. So I thought I'd just go through a little example in MATLAB just to show you how to basically create an array on the fly. So for this example here, I want to basically show you how to design a program that will create any array of a given size that I want to, okay? So again, is that readable for everyone? I can increase the font size. I'll make it a bit larger then. So in MATLAB, if you want to change the font size, preferences, fonts, and we'll make it maybe 16, 18. So how's that? Bit better? Okay, so this program is going to create an array of custom size, okay? So the first thing I usually do is clear the command line, and then I clear the workspace with those two commands. Now let's say I just want to get the number of rows from the user. Get the number of rows from the user. How do I do that? Anyone? Input function. Input function is what I'm looking for. So it's going to be rows is equal to the input. How many rows? So it's going to pause at that, grab the number from the user that we want, and store it in the value rows. Let's do the exact same thing for columns. So get the number of columns, and we're going to store that in a variable called columns using the exact same method. Rightio, pretty simple. Now what if I wanted to create an array with that number of rows and that number of columns? How do I do that? Zeros is a good function. Zeros allows us to create an array of whatever size we want and put zeros in every single element. Okay, so let's do that. Let's call this array, we'll write our comment first. Create a 0 array of given size. And we're going to call this array just like that. And it's going to be basically the zeros function, and it needs for an input rows and columns, the dimension of our array that we're going to have. Rows, cols, and that array is going to be full up to zeros with whatever size we specify. But what if we want to put values of our own choosing in every single spot in that array? Like we want to iterate over every row, every column, and ask the user, what value do you want to put in this element? How can we do that? It's an iterative process, right? I would use a for loop. So let's say I want a loop for every row, and that would be for I equals, row is my, I is my row counter. I've just created it. It can be any name. For I equals 1, 2 rows, the maximum number of rows that we're looking to iterate over. And then while we're in each row, we want to also iterate over every single column. Okay? So inside this for loop, I'm going to nest another for loop. Loop for every column. And the way I do that is exactly the same, although I have to use a different variable now, because if I use I again, it would mess up the other I. So we're changing it to j now, for j equals 1 to number of columns. And now we want to get a value from the user. Let's just call it val, and same thing, input function, what value perhaps. Close it off, and now we want to store this value in the ith row and the jth column of our array. How do we do that? Anyone? Yes?
Whatever your array number is.
That's our name, yep.
And then just reference it with ij as
Yeah, because the I is our value that's counting up what row we're currently in, and the J is the one for the columns. So we know at this given point, I is the ith row and j is the jth column, and we're going to assign a value that we just asked for into that position. So this value is going to be placed into that exact spot in the array. And that's pretty much it. We can end that, and one thing I'll do is just display the array, and we can just do that like so. So let's give it a run. First I've got to save it. I'll just call it array creator. How many rows? I'll give it 2 rows by 3 columns. And now we're expecting, right, to see, it's going to ask us for 6 values in total because we've got 6 elements to fill. So this is the first leftmost, topmost element. And I'm just going to go in sequential order. And now the 6th value, and it displays our rows accumulated, okay? So that makes sense, everyone? I thought it would just be useful to go through array indexing again because some of you are having problems in the lab. Hopefully it's a bit more clear now. Let's get back to our lecture notes. How do I do that? I'll just minimize this. And run PowerPoint. Cool. The other part was to vectorize code, and we've also seen that it makes your code more neat and more efficient. So coming up next week, we have our Easter break here, obviously, but after Easter break, assignment 2 will be released. Next week's lab will be numerical techniques. Okay, that's integration, differentiation, how we can simulate that with a computer. It's going to be very helpful for your assignment 2, which is the Jonathan Thurston Kick Simulator, because we're simulating projectile motion, and you're going to see how important that is in next week's lab. Quiz 1 will be held in 2 weeks, the 4th of April, that's a Monday, and I'll give you some more information about that in the coming weeks. For study, I'm going to upload previous week's lab solutions and also last year's quiz, so that you can actually study it in preparation for the quiz. But let's get on to today's lecture. So we're looking at number systems, but more in general, we're looking at, we're going to have a look at positional number systems, converting binary and decimal numbers, performing binary arithmetic, and representing negative numbers in binary format, which is going to be very useful. First, let's have a look at the different positional number systems we can look at. Before that, we should revise what exactly data types are. So characters, if you recall, are just text and symbol data types that are encoded into a numeric format so that a computer can actually understand them. MATLAB uses UTF-8 encoding, which is Universal Transformation Format for 8 bits. Okay, that's what that stands for. And it's useful because it's identical to that ASCII format, which is something else that we talked about, which means that all the English symbols are the exact same encoded letters. However, the UTF-8 format also has different language symbols and other different symbols like the Greek symbols that we used in this week's lab as well. Now that's characters. Strings are basically just an array of characters. And because they're an array, that means that we can manipulate them, index them like we just did before. We indexed the numeric array. We can index strings in the exact same manner because they're an array of characters, okay? So we can just manipulate a string by typing the string name, parenthesis, and grab the ith element from a string. Numeric data types, they're a bit different. So we have really 2 branches of numeric data types, okay? The first is signed and unsigned integers, and they're basically meaning to represent whole numbers, okay? And they can be whole, negative, and positive numbers. Signed means that it has a positive and negative difference. Unsigned integers mean only positive. That's all it can handle, okay? Everything above 0. However, we also have the floating point numbers. We're going to talk about these in detail next week. They're for representing fractional numbers. So when you have 1.5 and stuff in between. It's a bit more tricky for that, and we're going to talk about that the entire next lecture. But in the end, all data types are stored on a computer in binary form. A computer can only read numbers, and the most efficient way to do that is in binary. So we're going to talk in more detail about binary in particular. Binary is a positional number system, but the most familiar positional number system that we use is decimal, right? What's decimal? It's actually the base 10 number system, okay? So it's known as the base 10 number system. The base of a number system is just the number of unique digits that you can represent with a number, okay? So think about our decimal. How many unique digits are there? There's only 0, 1, all the way up to 9. As soon as we start counting to 10 and 11 and 12, we're reusing those same unique digits, 0 to 9, right? So there's only 10 of them. That's the base, and that's why we call it the base 10 number system. It's actually called a positional number system because the position of the digit within the number actually plays a part in the value, okay? Think about just the digit 5. If the digit 5 were in the rightmost position of our number, it's worth 5, right? But if we shift it over to one spot to the left, it's now in the tens column, right? So a 5 in that column would be worth 50. So on and so forth, it gets scaled up by a factor of 10. That's why we call it a positional number system. Keep that in mind. That same process works for binary number system and all the other different types. So the way we define the decimal number system, any whole number can be written as a linear combination of ones, tens, hundreds, and thousands. A nice way to represent that is with a table like this. We immediately look at our number. For example, the number 123 in base 10. It has a 3 in the ones column, a 2 in the tens column, and a 1 in the hundreds column. So if we write it all out, we can see how each one basically performs the linear combination to get our final value. It's also worth noting that we represent the ones column with a 10 to the power of 0. And we also call this the least significant column, or the least significant position in the number. As we move further and further left, that power gets raised up and up, okay? So I would say that the thousands is the 10 to the third column, and that kind of process, just try and train yourself to that, because by understanding how it works for that, you can apply it to all the different number systems that we're going to be looking at. But it begs the question, what does a different number system look like if we change the base? We know what it looks like for base 10. What does it look like for a base n? We call it base n because it just n represents any number. And it turns out that we can define any number system in the exact same way. The number 1, 2, 3 in a base n number system can be written as 1, 2, 3 in subscript n. That's telling us I'm writing this number in base n, okay? So that number 1, 2, 3 is not equal to 123. It's only equal to 123 in base 10, okay? So this is important to note. But the number 1, 2, 3 in base n is going to be equal to 1, because that's in the third digit, multiplied by the base n to the power of 2, plus 2 multiplied by n to the power of 1, and so on and so forth. So it's actually quite easy to convert from a base n number system into a base 10 number system, because the additions we're doing are the ones that we do for our whole life. So for example, to convert 3, 2, 4 in the base 5 number system into the base 10, all we have to do is calculate the values of those 3, 2, and 4 based on their position in the base 5, okay? So remember, if that 3 is in the third column in a base 5 number system, we have to multiply it by 5 to the power of 2. And then for the 2 one, it's actually in the 5s column. So that 2 is multiplied by 5 to the power of 1. And the least significant digit is 4, and that's in the 1s column, which is 5 to the power of 0. So the addition becomes 3 times 25 plus 2 times 5 plus 4 times 1, which equates to 89 in the base 10 number system. It's important to understand this notation here. 324 in base 5 equals 89 in base 10. The reverse is actually a little trickier. So if I wanted to convert from a decimal into a base n number system, you actually have to do some repeated divisions, and it requires a couple of tricks in order to make it a faster process. The way you do it is you repeatedly divide the number by the base, keeping track of the remainders. So let's just step through it. So we have the number 89 in base 10, and we want to convert it to base 5. We take 89, divide it by our base, which is 5. The result is 17 with a remainder of 4. That's telling us that we can place 5 into 89 17 times, and we'll have 4 left over, right? So then we just take the number 17 and divide it by 5. The result is 3 with a remainder 2. Then we take that 3, divide it by 5. It gives us 0 with a remainder 3. We keep doing this process until it stops when we get a division result of 0, okay? That's telling us we've stopped, and now we need to grab our number out of the result. The trick is our number in base 5 is just the reverse of the remainders, okay? So we take the 3, the 2, the 4, put them together, and that's our value in base 5. There's mathematics behind that, but for now, just be familiar with the process. We can go through the maths in our labs. But why is it that taking the reverse order gives us the correct result? That's a fair question to ask. It's because the first remainder is the least significant digit, and again, that begs another question. The reason for that is when we divide by 5 once, the remainder is part that doesn't fit into 5 by 1. So instead, it has to come by 5 to the power of 0, okay? So basically, in that 5 to the power of 0 column, you can never have a value that's larger than 5, so it has to come under there. Similarly, when you divide by 5 again, the remainder is the part of the number that doesn't fit into 25, or 5 squared. And as a result, it must come under the significant digit 1 next to it. And so on and so forth. That's how that process actually works. So that's positional number systems. Now we'll look in more detail about binary and decimal, because that's probably the most important conversions that we have to make. So number systems in computing. Computers use binary. The binary system is just the base 2 number system, okay? It has 2 possible values. Do we know what those values are? 0 and 1. There are 2, and it's 0 and 1 by convention. Any idea why computers use binary?
Because they're based on PNP transistors that have on and off that represent 0.
Exactly. It's the on and off of digital electronics is the reason why computers basically, it's more efficient for them and it enables them to communicate with hardware, right? By being able to represent a high voltage and a low voltage with a 0 and a 1 number system, it allows a computer to actually talk to electronic devices. So it's a fundamental part of computing, okay? So a 0 basically always represents a low voltage or off, and a 1 always represents a high voltage or on. So the binary number system is the natural language of a computer basically. And we have a little video here that demonstrates how and why computers are basically read in binary.
No doubt about it. This place is haunted.
Don't be silly, mon. The last ghost died over 200 years ago.
The last human ghost. But robot ghosts... Ah!
0101100101. What does it mean?
It's just gibberish. 101001101010. Ah!
There you go. So obviously, all the humans are confused. They have no idea what's going on, right? Why is that? Yes? They can't. They can. Like, we're going to be able to, obviously, but on the fly, we can't do it like that. So the reason why Bender was also so scared is he's able to read the numbers in binary automatically, and the unmirrored copy of that number was just gibberish. It was 357 in decimal format. But Bender automatically converted it into the decimal number, which actually is 666, which is the number of the beast. I still don't know why he was so scared, but that's the reason mathematically why it happened, okay? So it's also useful, it shows when we have to and why we should convert between base 2 and base 10, okay? It's an important thing that we're going to have to do on a regular basis. So this is how we convert from a decimal number to a binary number. We do the same division process that we just went through. So we take 50, divide it by our base, which is 2 for binary, and we get the remainder 0 with a value of 25. We then take 25, divide it by 0, get our remainder, and so on and so forth until we get a 0 division result. And then we simply backtrack and store the remainders in reverse order. And that's the number in binary, okay? So that's how it works. It's a pattern that we've found to basically shortcut the process. So to convert the other way from binary to base 10, it's a little more easier, I would say. It makes a bit more sense visually. So to convert 101010 into decimal, we simply have to map out the value of each digit in the column that it's in, okay? So the rightmost digit is what we call the least significant digit. So in base 2, that's just 2 to the power of 0, which is equal to 1. It's the ones column, right? If we take one step to the left, this is 2 to the power of 1 column. Okay, what's 2 to the power of 1? It's 2. So that means that second column is the 2's column. We keep going forth by powers of 2, and we have the 4's column, the 8's column, 16's, and 32. So all we have to do is work out how many values basically for each column is taking part in this number, okay? So if we just basically write our decimal, our binary number into those tables, it's just a simple multiplication. There's a 1 in the leftmost column, so we take 32 into the sum. There's a 1 in the 8's column, so 8's in the sum. And then there's a 1 in the 2's column. So the sum simply becomes 32 plus 8 plus 2 equals 42 in base 10. We're going to go through a number of these examples, and they will be on the quiz. A simple question of convert this number to binary, that's going to be on your quiz, okay? So it's important that you get used to this process. This table here basically shows the different binary conversions for the decimal numbers from 0 to 7. So as you can see, there's a pattern on the right in those numbers. The important thing to note here is that we can only represent those 8 numbers from 0 to 7 with 3 bits. Okay, remember a bit is just a single binary value. So those values on the right, because there's 3 binary values, they're called 3-bit numbers, okay? If we wanted to get a number larger than 7, we would need to have more bits in this binary format, okay? There's no way that we can represent a number other than these ones with less than 3 bits. Which brings us back to using binary in practice. We are limited. We are limited in the use that we can actually make of it. So inside a computer, binary numbers have a fixed number of digits or a fixed number of bits that we can use. And that makes sense, right? Whenever you need to store more data, you're going to need more kilobytes of space or more megabytes of space. That's just how it works. So if you need to store a larger number, you're going to have to need a larger bit number in your binary value. So common sizes of binary variables, they basically are by powers of 2. We have an 8-bit binary variable, 16 bits, 32 bits, and 64 bits. The reason why we do powers of 2 is because it makes it easier to convert between different variable types, okay? If we had something that was 15 bits, the conversion from 15 bits to 16 bits is quite difficult. Whereas if we have it by powers of 2, it's a simple shift in our columns, okay? That's just the nature of the binary format. It's a lot easier to convert between powers of 2. All it takes is a shift of the digits. It's also important to note that 8 bits makes up a byte. That's a common representation that we use in computing. And there are a number of binary prefixes, much like with meters, kilometers, and millimeters. We have the same prefixes for binary values. So for typically, they stand for 1,000, right? So 1,000 bytes is equal to 1 kilobyte. 1,000 kilobytes is equal to a megabyte, and so on and so forth. However, what I just mentioned was that the common usages of binary values are powers of 2. 1,000 is not a power of 2. So this is actually an approximation that has been used, and you'll see it. This is why kilobytes and megabytes and gigabytes have become popular, just because that's been used forever. But it's actually inaccurate. The computers always use a power of 2. And instead of 1,000, it's actually 1,024, okay? So the preferred IEC nomenclature, I believe that's the Institute of Electrotechnical Commission, something, yes, I'll look into that, uses multiples of 1024. So this is the true basic data forms. And 1024 bytes is actually equal to 1 kibibyte. And they specify it with a lowercase k, I, and a capital B for byte. You may have seen these before. You see it vary. Some people use kilobytes, some people use kibibytes. It's actually quite confusing when you're trying to purchase a hard drive or you're trying to find your right internet speed, because some specify in KIB, some specify in kilobytes, and you're paying money for something that you know you might not be getting, right? You might be getting a different speed or storage space than what you would be expecting. So it's worth keeping in mind that there are 2 different versions. This one is the actual one, and this one is short changing you. So unsigned integers, that's a data type that we use to represent positive numbers, positive whole numbers. They are always a fixed size in binary numbers. The maximum value that can be represented by an 8-bit unsigned integer is a 1 in every single column. That's the maximum digit that we can use, and if we put that into every single column, it's going to be 2 to the power of 7 plus 2 to the power of 6 plus 2 to the power of so on and so on and so on, and that result is 255. So I asked the question, what is the maximum value that can be represented with a 16-bit unsigned integer? So think about it. We're going to have 16 locations. All of them are going to have 1 in it. And it's a sum of 2 to the power of 15 plus 2 to the power of 14, so on and so forth. Any ideas what the number is? Anyone have a calculator? No. So that value is 2 to the power of 16 minus 1. And that's equal to 65,535. This tells us that the range of a 6-bit unsigned integer can go from the value 0 to up to the value 65,535. Outside of that, we cannot represent any number outside of that, okay? So in general, the range of an n-bit unsigned integer is from 0 to 2 to the power of n minus 1. There are some shorthand binary notations that we can use for our own benefit, because doing these calculations can be like taxing, right? Writing out all those ones and zeros for large numbers is just not practical. So what we can do to shortcut that process is use a number system that's a power of 2, because the conversion is quite simple, and we can reduce the number of space it takes to write a binary number. So two common ones that we use to convert to are called Octal, which is just base 8 number system, and the Hexadecimal, which is base 16 number system, okay? And computers use these a lot. So for Octal, all we have to do to convert from a binary value to an octal value is separate the binary number into groups of 3 bits. Any idea why it's 3 bits for an octal number? 2 cubed. That's right. 2 cubed equals 8, and it's an octal number system, which means it has a base 8. And the 3 in the power of tells us we need to get 3 individual bits. So each group of bits represents a single octal digit. So let's do this conversion right here. In red, we have the first 3 bits of our binary number, and we pull that to the left, and that's equal to, in binary, converting it to decimal, 2. And then the middle one is 111, and that's 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0. That equals 7. The one on the right is just 2 to the power of 1, so that's 2. Then you just slam those 3 values together, 272, and that's our octal representation of that binary number. For hexadecimal, hexadecimal is base 16. So it separates the digits into groups of 4. That's because 2 to the power of 4 equals 16. Each group of bits here represents a single hexadecimal digit. So then we ask the question, how many symbols then do we need to uniquely specify every possible combination of 4 bits, okay? Does anyone have an idea there? So that basically means for binary, we needed 2 symbols, right? We could only represent 0 to 1. For octal, we needed 7 digits because we could only represent there to there. So for a 16-bit, for a base 16 system, how many symbols do we need? Any idea? It's 16 minus 1 because we're counting the values from 0 to 15. So we need 2 to the power of 4 or 16 symbols. 16 symbols. As a result, we use the first symbols from our numeric form, 0 to 9. They make up the first 10 symbols. And then we need 6 more symbols. So we use A through to F. Okay? And that's where we get those values from. Here we have a table that shows us all the different binary and hexadecimal conversions of the first 15 decimal numbers. So we have 0 to 15 and their accompanying binary and hexadecimal formats. Again, if I wanted to store a number that was larger than 15, I would need to add in another bit. This is all we can represent with 4 bits of data. So that's it for converting binary and decimal numbers and hexadecimal numbers. Now let's look at binary arithmetic, okay? Because the computers use these values to perform different calculations. Arithmetic just means subtraction and addition. So let's look at some subtraction addition with binary numbers. It works out that arithmetic is exactly the same across all number systems. Pretty useful. Consider this binary addition right here. I'm going to step through it in a little bit. But how do we do write out normal decimal addition, right? We go to the least significant bit on the right. We add up our 2 values. And if it overflows what can store in that little bit, we have to carry the 1, right, into the next digit. Carrying the 1 means we're moving by a factor of 10 into the next column. For binary, we can only count up to 0 to 2, or 0, 1, representing 2 values. So we add our first digits on the right and carry over the 1 if it's equal to or greater than 2. When we add large enough numbers together, the digits overflow, as I talk about, and the most significant bit is carried. So let's step through this calculation. So first we want to look at the sum of these 2 values, right? 1 plus 1 in binary, what would that be? 0, well, 1 in binary is equal to 1 in decimal. It's exactly the same for binary and decimal because there's no overflow or anything like that. So the value is actually 2. But we can't represent 2 in binary. How do we represent 2 in binary? 1, 0. So as a result, we have to place a 0 on the bottom and a 1 to the next column. The 1 is carrying over. Whenever we go above the value of 1, 2 and more, we have to carry over our values to the left, okay? So now we have the sum 1, 1, 0. Again, that's just 1 plus 1. So we throw a 0 down, carry the 1. Same thing, although here we're going 1 plus 1 plus 1. That's 3, right? So what's our answer? 3 in binary form. It's not 11 because 11 indicates that there's a 10 factor, right? It indicates a base 10. So it's best to say 1, 1 in binary format. So that gives us a 1 and a 1. We carry the 1 and we place the 1 down. Now we have 1 plus 1 again, 0, 1, 1 plus 1, 0, 1, and again the same thing here, 1 plus 1, and now we have another 3. And also we're at the end of our basic, at the end of the number of values we have. So we do what we do in a standard form. We carry over our value and it just becomes placed to the leftmost part. So it becomes 1 and then 1. And that's our result. Okay? Takes a bit of getting used to, but the method is identical. The method is identical. So that's binary arithmetic. It works the same for subtraction. Now let's look at a very important thing, and that's representing negative numbers in binary, okay? It's not as easy as you might think. It's actually quite difficult, and people have been working out solutions to this for a long time. We're going to go through 3 different solutions today, but let's just first look at it. In written form, for us, negative numbers are easily represented by putting a negative sign at the front, right? Makes sense to us, but how does a computer interpret that negative sign? How do they encode a negative value such that it can use it in calculations? Any ideas? I don't think so. We use sign magnitude, that's one method. Excess n is another method, and 2's complement, which is perhaps the best method, okay? So these 3 methods have been developed over time, and one of them is better than the others. We're going to show you why. So the first method, sign and magnitude, also called sign magnitude. It basically involves what the name suggests. It's going to store the sign of the value, which is our negative or positive. So it's going to need a 2-value variable to do that. And it's also going to store the magnitude. So if it's 5, it needs to store the 5. If it's negative 5, the magnitude is exactly the same, except the sign has been swapped. So the way that we do that with a computer is we choose 1 bit to represent the minus sign. Any ideas why we can use a single bit? Because it's a state of on or off. It's positive or negative. So we only need to waste 1 bit with that sign, okay? Everything else can be used for the magnitude in our variable. So an n-bit integer will have n minus 1 bits for storing the magnitude and 1 bit for storing the sign. For example, the number 5 in base 10 is represented by, we're using the leftmost digit here to represent our sign, okay? So if it's a 0, it represents a positive number, and if it's a 1, it represents a negative number. So, the 5 in binary is just 101. That takes up our 3 least significant bits on the right, and the leftmost bit is a 0 because 5 is positive. The counter example is negative 5. So we flip the sign bit, which is the leftmost, to a 1 because we want it to be a negative number, and the magnitude stays the same. It's 101 because that's what the binary representation of 5 is. Question?
If you didn't know there's a negative, how would you know that 1 doesn't count as like that?
Yep, so the computer has a way, basically, before we use these numbers, the computer is told the leftmost bit is our sign bit. Analyze it differently to the other 7 values. And that's actually a negative point about this method, okay? We have to tell it specifically. Don't look at the 8th bit, look at the 7 bits for the magnitude. So it's an inefficient manner of doing it, but that's how they do it, okay? So the benefits of sign magnitude. It's easy for us to understand, it's easy for us to read. Yeah, we'll just flip that bit. But for a computer to actually know which one it's flipping is inefficient, okay? But that's about it for the positives. The negatives of sign magnitude is that it has to be handled separately. Computers don't like doing it. And also the overflow of when we do an addition, it will affect that sign bit as well. So if we were doing a standard addition before with a negative value, there's a chance that that could overflow and mess up our sign and gibberish the data, right? So we'd have no idea what the value would be. That's a negative. Subtraction is also hard, and another negative here to note is that there are 2 zeros. Okay, that means there's a positive 0 and a negative 0. Again, this is an inefficiency. The computer has to deal with 2 bits of data rather than a single one, okay? So it's an inefficiency for the computer and it's a negative of this method. If we wanted to add negative values, we need the arithmetic to be the same regardless of the sign, because that's how computers really want to operate, okay? They don't want to have to change anything for an addition based on if its sign is a different value, okay? In order to be most efficient, it has to be the same. So for example, let's subtract 1 from 3 in 4-bit sign magnitude, okay? So we're saying we're in 4-bit sign magnitude. That means the leftmost bit is the 4th position, and it's going to indicate whether it's a positive or a negative, okay? So 3 minus 1 becomes 3 plus negative 1. So let's represent 3 and negative 1 in binary form using that 4-bit sign magnitude. The left, it's a positive, so the first bit is 0. 3 is represented by 1, 1. The rightmost number, negative 1, obviously it's a negative, so our first bit is 1, and then 1 is represented just with a 1 in the rightmost column. So if we were to add these with the same method that we did before, carrying the 1 at each step, we would end up with this value. What's that value in decimal using our 4-bit sign magnitude? The first bit is a 1, so it's a negative number. 100 is the magnitude. 100 in binary is just 1 in the 2 to the power of 2 column, so that equals 4. So our result here is negative 4. And as you can see, that's incorrect. 3 minus 1 should be 2. So by using sign magnitude, addition has been messed up. We need a special routine to handle this kind of addition, and that's not ideal. So let's move on to the XSN method. So for the XSN method, we just shift the number line away from 0. This means rather than having to deal with going positive and negative, we're just shifting all our values along the number line up to a larger value such that the addition and subtraction will work as normal. This means that the 0 in a base 10 is no longer the 0 in a binary because we've shifted by n. And yes, we shift by n, so we have to keep that in mind. The conversion from a decimal number into an 8-bit XS128 system is shown here. In order to convert to binary, we just shift the value 128 first. So we take our negative 30 and add 128 because it's our n value. That gives us 98. And then we just encode the 98 into binary form. And that's our representation. To convert the other way, we just have to do the reverse process. This involves first converting the number to a decimal and then subtracting 128, okay? And that's how we can get it back to that form. The benefits of this method is that the positive numbers are always larger than the negative numbers, which is useful. Another benefit is that the number line is always going in one direction. And there's only one 0. So it looks pretty good. But there are still some problems. The 0 is no longer at 0, which is a problem. Arithmetic no longer works because of that. Because of that single factor, the arithmetic is a bit muddled up as well. So let's have a look at an example. Let's calculate 3 plus 4 in 4-bit XSN. So what we're doing with XS8 is we're adding 8 to our number before converting it to binary. That's all we do. We add 8 to the number before converting to binary. Whoops. Let's go there. So 3 plus 4 becomes 1011 plus 1100. As a result, the overflow would go forward and it would also generate an error and give the incorrect result. So instead of being 7, it gives -1. So for this method, we would also need a special routine. This brings us to our best method. Let's just have a quick look. Our best method, which is 2's complement. This method is used by all the computers that you use, basically, okay? This is the best one. It doesn't have any problems, and it has all the benefits that we're looking for. So, we need a representation that provides consistent arithmetic behavior across an entire range of numbers. This is what we're looking for. 2's complement came up with an idea. Whoever came up with it, it was a great idea. For an n-bit integer, 2 to the power of n is just outside of the range of values that we can represent. Does that make sense? Because for an n-bit integer, the largest number we can represent is 2 to the power of n minus 1. So 2 to the power of n is just outside of all the values that we can actually represent with n bits. As a result, if we were to just convert 2 to the power of n into an n-bit integer, the value would be 0. It's a nifty little value that basically helps us to do 2's complement. For example, 2 to the power of 8 is equal to 1 with 7 trailing zeros in binary. And if we truncate it to just have 8 bits, we'd remove the 1 and all we're left is zeros. Therefore, if we were to say that any n-bit number x here is any n-bit number. If we take x and add 2 to the power of n and then subtract x, because 2 to the power of n is 0 in 8-bit number, this will equal 0. What's the benefit here of this x plus 2 to the power of n minus x? The reason why that's good for us is because if we take a number and add it by another number and it equals 0, then that other number has to be the negative of our x value, right? So as a result, we can therefore say that 2 to the power of n minus x is equal to the negative value of x. So we define the 2's complement of x as 2 to the power of n minus x. And adding these two values gives 0, and that tells us that it's a correct negative representation. So the benefits of 2 complement are that adding numbers will work for all the values, and there's actually no need to handle any explicit cases. This means that it's the most efficient method, and it works for everything. It also means subtraction just becomes the addition of a negative value, which is exactly what we want. There's only one 0, which is another benefit, and it's also the standard format used to represent signed integers in most computer processors. So let's look at how we actually convert a value into 2's complement and vice versa. So the way we do that is we need to find out the weight of all the digits, okay? So we have our binary number. The way we translate a binary number into we have a decimal number. The way we translate a decimal number into a binary number is that we find out all the values of the binary digits. So in 2's complement, the leftmost digit is equal to negative 2 to the power of the position that it's in, okay? For in this case, for an 8-bit number, it's negative 128, because that's negative 2 to the power of n minus 1. And as a result, the range of n-bit 2's complement numbers can go from negative 2 to the power of n minus 1 all the way to 2 to the power of n minus 1 minus 1. It's a bit of a mouthful there. Just know that we're basically splitting our values. We have the same number of values that we can represent, but we're splitting it so that half the values are negative and half the values are positive, okay? So we can represent an 8-bit number with an unsigned integer, which is all positives, from 0 to 65,536. But for a 2's complement number, it's going to be half of 65,000 in the negative direction and then half in the positive direction. So this is the process to just do a conversion between 2's complement. To represent a negative number in 2's complement, all you have to do is 3 steps. Write the number's magnitude in binary. So if it's a 5, it's just 1, 0, 1. Then all we have to do is invert the bits. Go through there, swap zeros for ones and vice versa. And then we add 1 to that binary value. That's our shortcut to find 2's complement of any negative number. So here's an example. Let's represent the value negative 12 in 8-bit 2's complement. So because it's 8-bit, that's telling us we need to put 8 individual binary values next to each other. That's going to be our calculation sort of threshold. So 12 in the magnitude of 12 in binary, what's that? Anyone? It's going to be in powers of 2, 8 plus 4. 8 is 2 to the power of 3, so we put a 0 in the 3 plus 1th column, so it's just going to be 1, 1, 0, 0, which is 2 to the power of 3 plus 2 to the power of 2 gives us 12. Next step is to invert all the bits, so we go through, swap zeros for ones and vice versa, and then we just add 1. So if we add 1 to that second last line, 1, 1 becomes 1, 0, 0, and that's our negative representation in 2's complement. I know you're staring blankly at the screen now. You have to practice these, okay? And so I'm going to advise you to watch the screencast for next week. The screencast for next week go through every single type of conversion that we've looked at today in detail, and you can practice them yourself. We're going to have to get familiar with them, so I advise you to watch the screencasts and practice every single conversion yourself. To convert back to decimal, we basically have to write out our table of values. And again, the leftmost column in 8-bit is going to be negative 2 to the power of 7. So that's negative 128. And so if we have the binary number 4 ones and then 0, 1, 0, 0, we just put them into the column under the value that it should be under, okay? So as you can see, the third line in this table is our binary value, 1, 1, 1, 1, 0, 1, 0, 0. Then we add up all the different weights for each value and we get a sum that is negative 128 plus 64 plus 32 plus 16 plus 4 equals negative 12. So that's pretty much it for today. We've learned basically a lot of things. We've learned how to convert between various positional number systems. Positional means it depends on the position that it's in, the value. We've also learned to perform addition and subtraction in binary. We've converted binary numbers to and from octal and hexadecimal, and we've represented negative numbers using those 3 methods, of which 2's complement was the best. As I mentioned, the additional resources for this is week 6 screencast. You should be looking at them because they give you a number of examples doing a number of different conversions of these ones. So if it looks difficult now, practice it, watch the screencast, and it should kick in. Before you start packing your bags, you might want some information on quiz 1. So it's 2 weeks from now, Monday, the 4th of April. It's going to be 15 multiple choice questions, okay? It's going to take 45 minutes to complete, and it's going to cover all of the content from now to week 1, okay? So only the questions on the quiz will be up to week 1 to now. From here on out, no other lectures will cover material that you'll be quizzed on, okay? So quiz 1 only from weeks 1 to week 6. The resources for your study, I suggest that you look at the lecture notes, the labs and the screencasts for the first 6 weeks. And I'm going to upload last year's quiz for you to get more study resources. Thanks. Enjoy your Easter holidays.